Friends, welcome back to my channel. Today we will discuss a very special topic about transformer. If we see this transformer, it is working at the same line voltage 220 volts. These voltage are converted into DC and then it will switch that voltage. This is working directly on AC voltage. What is different between this transformer and this one? Basically, it is a question from my viewer Ishfaq Khan Shinwari. He is writing, "Hi dear, thanks for informative videos. I asked a question from many persons about the chopper, this transformer, which is being used in switch mode power supplies, high frequency switching. But nobody satisfied me. When we check the chopper, there are very less winding. How they create that much volt and ampere? When we check by multimeter, it is 0 ohm. Okay, let's see it. I will try my best to explain. I will try to explain in the simplest way, and I hope you will follow that. If we see this transformer, when we say transformer, that means it have primary winding, secondary winding. Either it is step up, step down, but it is transformer. That means some current will flow here, second current will flow here, secondary side. So it will provide isolation. There is no physical electrical connection between this winding and this winding. How it works? It works on the magnetic flux. When the current will flow in the winding, it will create magnetic field. This core will magnetize. So it will become a piece of magnet, but its magnetic poles will change at change in electrical current. If we are switching at 60 Hertz, so its magnetic poles will switch at 60 Hertz. But imagine, if the same magnet we will rotate at 60 kilohertz. If 60 Hertz, that means 60 times in 1 second. If 60 kilohertz, that means it is 60,000 times in 1 second. So this changing magnetic field, when its poles are changing, this changing magnetic field will cut this winding. It will create voltage. If the magnetic field is changing slowly, it will create less voltage. If the magnetic field will change fast, it will create more voltage. Let's take example. We have a generator. It have permanent magnet. When the generator shaft will spin slowly, it will produce low voltage. And that generator needs a specific RPM to produce 220 volt or its rated voltage. In any generator, we need standardized RPM, rotation, to take that standard output. Now we will take this key point for these transformers. When this magnetic field is changing slowly, it will produce low voltage, less power. When there are less induction, low induction, it will create low power. And if we change that magnetic field with fast speed, in generator the magnetic field was stabilized. Here winding is stabilized, we are spinning the magnetic field. Now we will see from some different angle. The point in the question that when we see the winding, it have few turns. Yes, it have very few turns. For example, it is using 150 turns. And maximum length of this wire, we can say it is 1 meter, 2 meter. And if we see this transformer, maybe it is using 100 meter. For example, here and here, this and this. What is the difference here? If we see, it is large size and it is in small size. If we say this one, maybe it is providing 12 volt, 2 ampere, we can say 24 watt. And this one, might be it is providing 12 volt, 2 ampere. Size small, power equal. When we check its resistance is, we can say, around 100 ohm to 1 kilo ohm. And its resistance, it will around, we can say, 1 ohm. Here 100 ohm, here is 1 ohm. Imagine this one we are connecting to 220 volt RMS. And when we connect the same supply 220 volt to bridge rectifier, it will produce approximately 310 volt DC. Now we are connecting this 310 volt to this transformer. Here we are providing some frequency. Difference here, it is working at 60 Hz. It is working at 60 kilohertz. Its magnetic field will change 60 times in 1 second, and its magnetic field will change in 60,000 times in 1 second. This is a piece of wire. We are discussing DC resistance. I told here its resistance is maybe 100 ohm to 1 kilo ohm, 2 kilo ohms. This transformer primary side resistance is 64 ohms because it is providing high amperage in the output, so it is using 64 ohms. Normal transformers 100 ohm, 200 ohm, 500 ohms, like that. But if we will check this transformer, its primary winding is just only 0.7 ohm. So 0.7 and 64 ohms, it have a big difference. This is DC resistance. We will not consider this resistance because when we say a piece of wire, it is just only 1 meter piece of wire which have resistance, we can say just only 1 ohm. But its resistance will increase when we will place core here. This core, it have a special role in this transformer. This transformer, it have 2.06 Henry. It is working in 20 Henry range. So 2.05 Henry. This transformer 2.05 Henry. And if we will check this one, it have 1.56 millihenry. 1.56 millihenry. Big difference. Its resistance is DC resistance 64 ohms, and its, we can say, 0.9. We will consider 1 ohm. Okay. Now the main role here comes for this core. If we will measure DC resistance with ohm meter, it will remain same. But now if I will connect, for example, this piece of wire here, it is 0.14 118 microhenry. Now I will place just only 1/2 of the ferrite core. Its inductance increased up to 233. If we will place more core here, as I added one screwdriver here, so it is 300 microhenry. Now it is just only 118 microhenry. When the core is added, its inductance increased. That means the core have special role here. When we say inductor is piece of wire. Its DC resistance is very low. When we will use it in DC circuit, it will use its DC resistance. But when we will use it in AC circuit, this is the biggest point here, that in AC circuit this inductor will provide XL, that is called inductive reactance. XL is equal to 2 pi FL. 2 pi, that is the changing current, that is the swinging magnetic field, then the frequency, and then the inductor size. If I am using this transformer, the large one, 2 multiplied by 3.14, that is the pi, and then F, frequency is 60 Hertz, and then the inductor value, that is 2.05 Henry. It will provide 772 ohm resistance at 60 Hertz. Note this point, that this transformer, it have 64 ohm resistance in DC resistance when we test with this multimeter, but when we will test with LCR meter, it will provide us inductance. This inductance 2.05, when we will operate it at 60 Hertz, it will provide 772 Hertz. Now come to this small transformer, this one. It have 1.56 10 raised to power minus 3 millihenry, but the frequency is now 60,000 Hertz, 60 kilohertz. At 60 kilohertz, it will provide 587 ohms. Here we are using, I can say, 500 grams copper. Here maybe we are using 20 gram copper. Copper size reduced. Core size reduced. Here we are using a large size bobbin, and here is very small tiny bobbin. And if you will see small transformers which are used in the mobile chargers, we can say that are equal to our nail, small size. If I will use this transformer at 100 kilohertz, at 100 kilohertz, its resistance will 979 ohms. We can say 1 kilo. At 60 kilohertz, 587 ohms. This transformer will work all the time, but this one will work in very small portions of the cycle. This is one cycle, and it will operate 60,000 times in 1 second, but this transformer will remain in action all the time. Now the second thing, what is the role of this core in the transformer? The material of this core is very important. When we apply voltage to this transformer, it will start to build magnetic field, and that magnetic field will reach in this core. It is using soft core, ferrite material, powder core, and this one is iron plates. When we will use this core, we can say this is a core, this is a razor rubber, and these are the magnetic flux lines. If we will try to enter here, we can say it is entering very easily. If I will try to enter in this hard core, that is this metal, it will feel difficulty. So this soft core, it allows easiest entrance to build magnetic field, that is called permeability of the core of this ferrite material. If it is using ferrite powder, if it is using manganese, zinc, or it is using some alloy cores, laminated cores, each material, it have its own permeability, its own features to provide easiness to the magnetic flux. So this core will allow to build magnetic field with easiness. So the magnetic flux will build easily. Here it will take time because it provides resistance to magnetic flux, but it provides easiness. So the operating frequency is the biggest difference. When the frequency will drop, its magnetic flux will not build properly, and this transformer will come back in DC region. When it is working at high frequency, it will work as a high frequency switching transformer. In any reason, if the switching frequency is dropped, it will behave like a piece of wire, so it will make short circuit. Why? At that time it will operate in DC region. Let's see some example here. I am using this transformer to switch. We can see I am providing 12 volts at 39 kilohertz and duty cycle is 0%. If I will increase the duty cycle, now we can see at 39 kilohertz, 14%, it is drawing just only 10 milliampere. I will increase the duty cycle, so the turn on time, which we discussed, that it will allow this time from here to here, or we are providing like this. At that time it is drawing more current. And if I will drop the frequency, this time the frequency is 36 kilohertz, 35. When the frequency will drop, we can see the current is increasing rapidly. When the frequency is 25 kilohertz, 250 milliampere current is flowing here. I will reduce more frequency. We can see the current is now at 500 milliampere. Half ampere is current flowing in this transformer now. If we will decrease more frequency, we can see at 9 kilohertz, around 1 ampere current is there. We can see this time at 6 kilohertz, this transformer is drawing 1.1 ampere current. That is very high current for this transformer. In this way it will damage. When the frequency will increase, now the current is decreasing. So this is the response. We can say now, if I will increase, let's say, frequency at 90 kilohertz, just only 200 milliampere is there, and duty cycle is now 36%. I will decrease the duty cycle. At 10% there is current flow, but this multimeter is unable to display because it is low current than the range of this multimeter. At 27%, just only 30 milliampere current is there. 90 kilohertz, 27%, just only 30 milliampere. Now I will decrease the frequency again. We can see the current is now increasing. When the frequency will decrease, the current will increase. So this is the important point for these transformers. So this is the important point for these transformers, that these work on very high frequency. When the frequency is decreasing, the current is increasing. When the frequency is at 3 kilohertz, it started to produce noise, a whistle sound. Now if I will increase the duty cycle, the current is now high and this power supply is now turning off. Why? Because it is taking too much current. I hope this video is informative. If it is informative, hit the like button. If you have any question or if you have some other explanation other than this, I will welcome. If you have any question, please write in the comments. Thanks for watching.